Right, guys, will you confirm if you can hear me there? And please, if this thing happens to cut the audio, please let me know immediately. Let me not realize in the middle of the session that I'm not audible. But please, 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 I ask, just confirm that I'm audible. Thumbs up, Yana, anyone there?
Sir, you're audible.
Perfect, thank you very much. All right, so in our previous discussion, we discussed really the idea behind functions and inverses. We looked at what is a function and why we have to kind of swap up the X and the Y story. We have done all that. So what I would like us to do today is just to add on to that and discuss in particular the inverse of the exponential function. So I thought maybe for today, before we just before today, before we just go far, let us plot some functions. Let's remind ourselves of basic things when plotting, and actually try and establish and find out what happens when we plot the exponential and we look out for the inverse. So I think that's what it would be a good idea to start with something like that, just to put us on the same page here. And in any case, I'm sure you want to know as well as to what really happens in a graph situation. So I'm gonna put up a graph here, and I don't have a grid. Well, with this software that I'm using, I'm still trying to get used to how things work here. So I'm delete this one. Great. And delete that too. Cool. So if I plot an exponential graph on the set of x's here, so obviously this is gonna be the x-axis, and this here is going to be the y-axis, right? So if I plot this thing, the exponential function here, I'd like you to take note of a few things. Roughly speaking, I could plot a graph like that. For argument's sake, let's call this the function y is equal to 2 to the x. Let's call it y equals to 2 to the x. Now, from last week's definition, we know that the inverse of this function will be defined by the function or the equation y is equal to log x base 2. So this is what we established last week. Now, if I sketch log x base 2, we know the theory says I'm essentially reflecting this blue graph here around this line y is equal to x. So remember, this one here is the line y is equal to x. This is what kind of explained why we have to do the switching. Now, let's just take some random points from the blue graph. One of those important points which we'll take, by the way, is this y-intercept here. So this is a 1 because x is 0 on the y-axis. Another name for the y-axis is literally the equation x equals to 0. Another name for the x-axis is the equation y is equal to 0. So that is why when we calculate intercepts, when we find the x-intercept, we make y 0 because y is 0 there on the x-axis, you understand? So that's one point that is quite obvious. If I want another point, really, I can just substitute x equals to 1. Of course, if I substitute x equals to 1, then I'll have y is equal to 2 to the 1, which is just a 2, right? So we could assume and argue, of course, my diagram is not drawn to scale, but we could argue that's a 2, because when x is 1, y is a 2. That's one point that I'm going to put in. Maybe another point. Let's have a point on the negative x-axis. If I put a minus 1, if I substitute a negative 1, then I'm getting, I think, a half. So then we could argue then that this point here is a half. Now, let's just write down the coordinates properly. We know we've got a minus 1 and a half. We've got the intercept, which is 0 and a 1. And then we have the point 1 and 2. The quickest way really to plot the inverse without even having to worry about this equation here in green, the quickest way to plot the inverse is to literally take these points and swap them around, because the principle says y equals to x. So I can just swap around the coordinates, and that should give me the graph of the inverse. Let's actually try that, and then we'll do the log later. You will see it matches. So if I swap around, let's look at the point negative 1 and a half. Negative 1 and a half. So maybe let's do it this way. Let's do it properly. And I want you to see this. If I have the point negative 1 and a half, on the inverse, it must become the point half and negative 1. So meaning half on the x-axis and negative 1 on the y-axis. Half on the x-axis and negative 1. It's pretty much something that's going to be there. I hope you see that little dot. I'm trying my best. Maybe let's take a normal pen instead of the calligraphy one. Yeah, that. Another one that I'm going to take is the point 0 and 1. So if I take the point 0 and 1, this has to change into 1 and 0. So it becomes 1 and 0 on the inverse, right? Let's take the last one, which is 1 and 2. This has to become 2 and 1. Now, let's plot these points. So I've got the negative, no, not the negative, but half and negative 1. I hope it's much clearer. Then 1 and 0 is right here. It's an intercept. And then the next one that I've got is 2 and 1. So when x is 2, y is 1, like that. There it is. Now I'm going to join these dots with a smooth curve, of course. And there we go. There we go. There you've got the inverse of the exponential. By literally just plotting points of the original and reflecting those points along the line y is equal to x. Just like that, you have your inverse. All right. And you, I mean, we can actually try this and see what happens when I have log. Let's do this so that you see it yourself. And I want you to try your calculator as well. I want you to try and see what happens if you plot in your calculator, not actually plot, but you kind of type in your calculator log half, you plot in log half base 2. I promise you, your calculator guaranteed will return a negative 1. That's what it will return. Let's say you take log 1. And if you were paying attention in the previous session, we said log of 1 is 0. There's no debate about that. You take log of 2. This one is quite so obvious. We spoke about it as well. If I take log 2 base 2, one of the log laws, I will definitely get a 1. So these are the two ways to do this. You can just generate points. And I want you to be, again, aware. I kind of tried to sensitize you here last week when we're doing the inverses. But I want to remind you that, remember, we said you never have a log of a negative number. So it's quite important to remind yourself here that x can only be greater than 0. And when we say greater than 0, we are just saying positive. And if you think of positive numbers, please beware that fractions, we do have positive numbers that are fractions as well. So I know students usually would think of 1, 2, 3, but you must remember there's 1.5, there's 1.2, there's even 0.1. 0.1 is surely bigger than 0. 0.25 is surely bigger than 0. 0.5 and so forth. So those numbers are also bigger than 0. We cannot exclude them because, remember, by the way, we work with the set of real numbers in normal mathematics. Excuse me. So it's quite important that we are aware of this, all right? If you can just remember the definition from first principles, as we discussed, that when we deal with logs, we cannot take a log of a negative number. If you can remember that, that's also going to help you. It will guide you so well as far as your, what is this? Domain. Yes, I wanted to say domain. As far as your domain is concerned. So I hope you really catch this one and you do not forget it at all. Right. Now, the next thing that we're going to do now is I want to actually look at the different cases, and I want you to note a pattern that sort of arises from this whole story. There's a pattern that's going to come, but we will note that pattern when as we do more and more problems. So I want to take another exponential form, which is maybe decreasing. I think this one is increasing. Yes, we will talk about that as well. You know, how do you tell if a function is increasing or decreasing? So those are other things that we will discuss. We just laying the foundation at the moment, right? So let's get to this one here. I want to sketch. How do I get a new page? Well, I'm going to extend this. There we go. Got it. So yeah, I still have my previous page. So again, let's quickly put up a set of axes here. Put up set of axes. Now, the next thing that I'm going to do here is I'm going to sketch, as I said, I'm going to sketch a different one, slightly different graph. And in this case, it's going to be a decreasing one so that we are versatile. You know, we need to know this in all sorts and forms as to how do we box it, all right? So now, let's sketch a decreasing one. So here it is. Let's try and make it nicer. Now, a possible equation to represent this, again, this is just a rough sketch. But if you remember your properties of functions and so forth, you will remember then that a possible representation of this graph will be something like this. Y is equal to, let's take a half to the x. Taking a half to the x. That's a possible representation of this graph, okay? I'm not saying it is, but let's take this one as one. Now, what we're going to do is we're going to look for the inverse. We're going to look for the inverse or the equation of the inverse. Again, if you remember the definition, you will note that there's two ways. We can either write the inverse as y is equal to log x base half. If you don't like this version of the inverse, you can go negative log x base 2. So these are your two options. And again, I guarantee you here that with substitution, you will see as we reflect it now that we're actually going to get a proper inverse. Okay, let's draw out our line of reflection. So I'm going to reflect this about the line y is equal to x. Let's give it some color. There's my line y is equal to x. Okay, now let's create points as we did it, and then we will also get to test it with the equation and see if actually there's a correlation here. We obviously know this is an intercept. It's a y-intercept, which means x is a 0. So this is the point 0 and 1, standard procedure with the exponential function. Now, I want to substitute a negative 1. If I substitute a negative 1, then the suggestion is that this point here will be a 2. So this must be negative 1 and 2. That is the suggestion. So you can even try this in your calculator and just substitute a negative 1, or raise a half to the negative 1. Just raise a half to the negative 1. I mean, as I always said, a half is 2 to the negative 1. And if you multiply those two exponents, negative 1, negative 1, gives you a positive 1. So that's how I know that it's going to be a 2. But you could, just to save yourself time, use a calculator. Now, let's take a positive 1 and see what's going to happen on the right-hand side. So if I take a positive 1, the suggestion obviously is that this number is going to be a half. So the point here will be, and I don't want it to lie on my red graph because that's so inaccurate. You know, that's the graph y equals to x, which means whatever the x value is, so it is with the y value. So let's try and be a little bit, well, let's try and make sense. Math must make sense. So let's try and write stuff that makes sense a little bit here. So if this is 1, then I've got here 1 and a half. I've got 1 and a half. So we said this line y equals to x literally swaps x and y values. So if an x value was 1, under this reflection, it will change to be a half. I'm just using the point 1 and half as an example, as an illustration. So let's do this now. We're going to swap every point. And again, I'll draw this in a different color. So if I look at the point negative 1 and 2, let's write a list of our points. The point negative 1 and 2 will become 2 and negative 1 under the inverse. All right. I see a hand here. Is there a question on the floor? Or was that by mistake? Was it Lisa or Lilita? Did I see a question? Are we fine? Okay. Silence is golden. Otherwise, you can text, right? So I've got negative 1 to 2, negative 1 and 2 changing to become 2 and negative 1. And we obviously know our favorite point, 0 and 1 is going to become 1 and 0. And then lastly, the point 1 and a half becomes half and a 1. So let's plot these and see what happens. So 2 and a negative 1 means I must be at 2 on the x-axis and a negative 1 on the y-axis. So this point is somewhere here. Now, when I look at the point 1 and 0, it is obviously an intercept here. Lastly, the point half and 1 is somewhere here. Half here, 1 there. So half is somewhere halfway here. We already have 1 there. Of course, like I said, I don't have a grid, so this is not drawn to scale. but I will figure out how to get a grid on this board. And then I'm sure your mind is giving you the inclination that your curve has got to go this way. There's no way your mind is not going, is not giving you that inclination. There's no way. It should kind of say, no, but this must be the picture. So now, again, as I said, let's test this and see. So I'm by the way, I'm showing you both methods so that you choose the most convenient method for yourself when dealing with this. You don't have to do both ways when you're in the exam, all right? You can either trust the equation which you have derived, the equation of the inverse. In this case, I am referring to this equation here. You can trust that equation, or you can say, no, let me get points from my original function, which is y is equal to half x, and let me swap those points. So again, someone might find it tedious, maybe long, to find points of the function then convert, and someone might find it just easy, of course, to find the equation of the inverse and then just derive points from there. But I'm just showing you both ways so that you actually choose the most convenient way for yourself. Now, if I substitute a 1, if I substitute a 1 in which graph am I going to substitute a 1 here? Okay, let me just write these points quickly so that we kind of, oh, but we have them there. Yeah. So by default, if I substitute a 1, I'm going to get 0 because we have established that log 1 is 0. So that's not an issue. If I substitute a half, I hope you do notice, if I substitute a half here, or by the way, when I say substitute, I'm talking about this equation here. So you see where I've kind of highlighted the x, circled the x, although that looks like a quad, but you get the point. When I hold a half there, when I substitute a half there, I'm gonna get a 1, and I leave it up to you to actually punch this on your calculators. You'll see that's the case. So this point is valid under this new equation. And if I substitute a 2, indeed, I'm actually going to get a negative 1. And it's easy to see this one by using this version of the equation of the inverse, because log 2 base 2 is a 1. So 1 times a negative, you're going to get a negative 1. So this point is also valid under this transformation. And what is interesting with this one, and now check the contrast. Look at what happened here. In this instance, your two inverses actually don't cross, don't meet. I want you to note that. And what is interesting with this one is that okay, I said two inverses, but the function and its inverse here somehow get to cross. And I think I've seen exam questions asking like, determine the point of intersection between G and its inverse and all that. And I mean, you guys can do logs, so that should be okay. This one might be a little bit of a mess to do it, but don't worry, we're getting there, and we will discuss those interesting questions. So if you are asked to draw, no, the y equals to x is not compulsory. Usually when you are asked to draw something, your marks will go for the shape of the graph, okay? And then you see, if you read questions around sketching graphs, they will say clearly indicate intercepts, points of intersections or any turning points, things like that. So when you follow those instructions within the question, you're actually helping yourself, because you are actually now meeting the marking criteria. Because what the marking criteria is going to check, okay, we spoke about intercepts in the instruction of the question. Does the student have intercepts on their graph? The shape obviously always matters. Is this thing drawn accurately? Does it show this correct shape? And then if it's two graphs and there's a point of intersection and they have instructed you to do to show that, they will also factor that in mind. So please, those are basic things that you need to always consider when drawing. All right. So for the log, 1 and 0 will always be an x-intercept, yes, because you are substituting 1 in the place of x, and log 1 by definition. You can even punch this in your calculator right now. Log 1 is actually equal to 0. So, yep, whenever you substitute 1 in the log function, you're going to get 0. Why is this true? Because for an exponential function, if you substitute a 0 in the place of x, you are getting 1. So I hope again you see the swap, the interchange there between x and y. Okay, Phil, that is that. Right. So this is another instance, and I hope you kind of see what happens. Don't just think, oh, there's no way they can intersect. No, there are actually instances where these two can intercept. So that is very crucial. But in general, what are we saying then? What are we saying? This is what I want to try and bring to your attention, having shown you these two examples. I want you to be aware of the following, that in general, if you sketch a log function and or an exponential function, the following happens. And I want you to see the relationship because, as I said, one is the inverse of the other. So I'm going to kind of put a contrast here. Okay. If I have an exponential function, and maybe let me talk about the log one first. So I hope you note the following. The graph y is equal to log x base a will look like this. So first thing to establish is that it exists on the positive x-axis only. Why? Because the log of a negative number is not known, is undefined. So that's very important. And then you just need 3 points to draw a log or an exponential. One of those obvious points is the intercept, and then the other one, watch this now, this is very key. I've been doing this point deliberately. Let me just bring to your attention the fact that I have never in this, or in all these points, I have never missed a point where you get a 1 as a result. And that was also deliberate. What do I mean by that? Remember, here it is. I've never missed this point. Log 2 base 2. Log 2 base 2 is equal to 1. And you're going to see as we do sort of integrated questions and advanced questions, you're going to see why this fact is important. So please take note of this. But another thing that I need you to take note of is this one here, where I've got log half as 1. And that's not an accident. It's actually a deliberate thing that I'm doing here. And I need you to be aware of it. Okay, let me bring this to attention as well. Please take note that log half base half in this case is equal to 1. And I'm saying this because now I want you to understand in general that you can always find 3 simple points easily for the log function without having to even use the table method. And these are the following. First of all is your intercept, which happens at 1 because you know log 1 is a 0. But the second one, which is quite cool, is the fact that right here, if you substitute the value of the base, you're going to get 1. Why? Because we have a rule, log laws. We have a rule that says log a base a is always equal to 1. Then another one that we discussed again, it's very interesting how these rules are coming together, is the fact that if I've got log of, let me start with numbers. If I have log x base 2, remember we have already agreed that log x base 2, not log x, log half, sorry, I'm not even saying that correctly. log x base half. My apologies. Yes. Log x base half. We have already established that log x base half is actually equal to negative log x base 2. We have already discussed that. Which means your third point that you can find, watch this, I hope you catch it. Don't miss it. Which means the other point that I can find for my log function, I can simply find actually by doing the following. By substituting 1 over whatever the value of my base is, and guess what? That will produce a negative 1. That will produce a negative 1. That is the interesting thing that has actually come up in whatever I was doing. So you can always get these 3 points. It's up to you how you want to do it. Now, what if a is a fraction? Basically, the base is a fraction, like here. Basically, I'm talking about this case here. How does this graph look like? Guess what? Let's just do it here. I'm going to do it on the same set of axes. So maybe let's put up the conditions. For this graph, we have a bigger than 1. Remember, the base can never be negative, by the way. And then for this graph, this one here, the purple one, we actually have, it can still be seen as y is equal to log x base a, but I need you to note that in this instance, a is between 0 and 1. So what happens in this case? So this is the cool part, very interesting. What happens is that this point here is actually 1 over a, but with a positive 1. And I guess you can guess what this point is going to be. Surely it's going to be a with a negative 1. I need you to see this relationship. In other words, you can just look at the log function as another function that you are learning about, okay? But what you need to note is that it has a strong relationship with the exponential function. And that relationship is the fact that the log function is the inverse of the exponential. And conversely, the exponential is the inverse of the logarithm. So I need you to be aware of these type of shapes that come up from the sketching the log function, all right? Because they will come there and you don't want them to catch you by surprise. I actually want us to do a question that kind of has this kind of stuff, so that we kind of get a sense of how this works out in an exam type of setting. So I'm gonna just put up a question here, and then we will then answer a few. Right. So I'm gonna write it down. I would have loved to type it. Okay, so what's happening here? Right. So I'm just gonna quickly write this, and then we look at how to answer it. Right. So it says the graph of f of x, and here we are given, or we are told that f of x equals to a to the x, and this graph passes through the point P with the following coordinates, a -2 and a 25. Then we are also told that there is a graph G, okay, which is a reflection. So G is the reflection of F in the line x equals to 0. You see, it's almost like I knew this would come later on. The line x equals to 0 is what? Is the y-axis. So don't panic. Just know your synonyms, know your terminology, and that these guys will play with the width and all that. Now, the first question is determine the value of A. So obviously they're talking about A in f of x equals to a to the x. I guess that one is pretty simple because all you need to do is you need to substitute, coordinates of a point, and then you can find that. So this one is not really a train smash. We can just go y is equal to a to the x. So I know that y is a 25 when x is a -2, something like that. And I'm going to write this as 1 over a squared. This is going to be fun. So 25 is 1 over a squared. Watch this then. A squared is 1 over 25, which means that a is a plus or minus 1 over 5. Of course, I've taken the square root. Now you got to make a call, right? What is the valid one? But looking at the shape, oh, by the way, I forgot to let you know or to show you this part. So they have kind of given us a drawing here. So let me just put that drawing. And while I put the drawing, Kumvana, you can just go ahead with your question.
So I wanted to ask, for the determining the value of A, why are we saying that 25 is equal to a to the power of -1?
Oh, sorry. That's a -2. My bad. My handwriting can be terrible at times. Does that sit well with you if it's a -2?
Yes.
So you understand where the -2 comes from.
No.
So look at the point P. They've given us the point P here with coordinates -2 and 25. So I have literally substituted the x values. The x value is a -2. Remember, for any point, you always have x coordinate and y coordinate. So I've substituted the x value, which is a -2, and the y value, which is a 25.
Okay. Thank you.
Sure. Cool. Right. So that's that. Now, looking at the shape, the red graph, by the way, represents f. So looking at the shape, you got to make a choice whether a is negative or positive, and surely a must be a positive 1 over 5, right? I don't know. What do you think? Remember, actually, maybe not even looking at the shape, actually, because that might be misleading. In fact, that's wrong. F is not that if a is 1 over 5. This should be f. My bad. that would have to be f, because look at this. Why am I saying this? Look at this. Look at half to the x here. Okay, so when the base is a half, your exponential graph is kind of decreasing. That theory must actually be very much correct. One reason you're going to take a positive a value of 1 over 5 instead of a negative value is the fact that the base is never negative. What can be negative is a multiplier, is a number that goes in front of the base. And by that I mean, remember, sometimes you have the exponential sk times a to the x. So what can be negative is this k value here, but the base can never be negative. We spoke about that when we were actually working out the inverses. So the theoretical principles must actually always go with our calculations. Okay, whatever we do in calculating must agree with the theory. Now, another thing, or the next question that they asked here was, if g of x is equal to b to the x, determine the value of b. Again, it's a conceptual question. So that's what they're saying. Suppose g of x. Now, this is the red one, so maybe I should use the red color. So suppose g of x is equal to b to the x. What should be the value of b? And again, I want to take you to this situation here, or maybe the situation here. And I want you to note that if you see the blue graph is y equals to 2 to the x. If I had to reflect this blue graph along the y-axis, it would have become this. That's what it would have become. That's what reflection on the y-axis does. So, and I'm bringing the reflection on the y-axis because they said to us, g is the reflection of f in the line y equals to x. So this is what g is. And I'm reminding you now that you need to remember what reflection on the y-axis does to the exponential function. And this is what it does, if I may write the rule. If your original function was something like 2 is to the x, and you reflect that on the y-axis, it actually becomes 2 to the minus x. So what reflection the y-axis generally does is the x values are kind of affected, right? So as you can see, 2 to the x, then you go where? 2 to the minus x. This is what happens. Watch. 2 to the minus x can be written as what? A half to the x. So the reflection in the y-axis just changes your graph from an increasing to a decreasing function, if you like. That's what you may say. So if you are with me here, I hope you will come to the conclusion that given that a is 1 over 5, b has to be a 5. I hope you get to that conclusion based on this relationship, because that is actually what reflection in the y-axis does, or reflection above the line y is equal to x. That's exactly what it does. So that's what b has to be. Now, another one is what would be the coordinates of p prime. P prime in this case is the image of p on g. So in other words, if I've got p here as a negative 2 and 25, the question is, what should be p prime on g of x? Given that g of x is a reflection of f in the y-axis, what changes? The y value stays the same and the x value changes, right? So instead of having p as a negative 2 and 25, you're going to have p as 2 and 25. So this is what I meant earlier on when I said reflection in the y-axis kind of alters, changes the x values. And that's exactly what happens here. The y value still remains 25, but x values have kind of changed. From a negative 2, we are now at a positive 2. So that's quite key. I need us to be able to do this kind of thing. Even for the log function, let me stress this, you should be able to reflect the log function either in the x-axis or in the y-axis and be able to come up with an equation for that. Okay, please beware of that. Okay. Now, the next one that I want to do is maybe show you a function, and I'm going to ask a question. That question will determine whether I will continue with the example or not. Somebody stay alert to answer this. So I've got a function, and here's how it looks like. It's sketched like this. So my question to you is, would you regard this as an exponential function or a log function? Is there anyone to answer that? You can even send it via text.
A log function, sir.
Well done. this must be a log function. So it's very good that you're noting those shapes. So now let's call this log function f of x. Let's call it f of x equals to log x base b. That's what it is. And it has a point here, a, and another point. Let's call this point, well, let's give it the coordinates 8 and a 3 over 2. Let's give it that. Now, without even having to do any calculations, what are the coordinates of A? What are the coordinates of point A? Do I have a winner?
Is it 0 and 1?
So if you are saying 0 and 1, this is what you are saying.
Oh, I meant 1 and 0.
Oh, 1 and 0. Okay. 1 and 0, then this is what you are saying. 1 and 0. And on that note, I will agree with you because we know by default that log 1 is 0. So this does not really require a debate. Log 1 is a 0. So we are using that property of logs. Okay, well done, guys. That's good. That's good. That's impressive. I am comforted in that we are catching this. This is not in vain. All right. Now, given that, let's see if you really captured this well. Can someone give me the equation of the inverse? Let's see. Have we understood this log exponential story? What would be the equation of the inverse? Is anyone there? Or are you still working it out? It's fine. I'll give you a minute to work that out. Anyone? Any taker? Okay, do you at least have an idea that the inverse has to be the exponential? Or is it because we don't know what b is? You can write it in terms of b. That's not a problem. Amandla?
So I was going to say the inverse is equal to f to the power of negative, what you've written there is equal to b to the power of x.
Right. That sounds good. That sounds good. F inverse is b to the x. I'm glad you corrected yourself there. We don't say to the power of f to the power negative 1. This reads f inverse. Okay, good. Good stuff. That's what it is. Now, if this is the case, I just want us to have fun here, guys. I really want us to have fun here. If this is the case, what should be the reflection of this point? Oops, now I'm erasing and I don't want to erase, I want to circle. So look at the point 8 and negative 3, right? So my question is, once I have the inverse, what would be the coordinates of this point on the inverse? The point 8 and 2 over 3. I'm hoping you kind of understand what I mean. Yes, Kumvana, go for it.
So, right, you said that the x value is the one that changes, right? So won't it be negative 8 2 over 3.
So, okay.
Would it not be 2 over 3 and 8?
Exactly. Exactly. Now, Kamvana, I want you to note something. There's two reflections that we have done here. We have reflected in the previous question, we were reflecting in the y-axis, which is the line x equals to 0. And that's why the x value was affected. But now, the moment we talk the inverse, please be aware of the fact that we are actually reflecting in the line y equals to x. And that is why what's going to happen is in the inverse, this point here will have the coordinates 2 over 3 and 8. We just literally swap them around. That's that. So please note the differences between reflecting in the x-axis or y-axis and reflecting about the line y equals to x. There might actually be a conceptual question which goes like, they give you two graphs and they ask you, how would you reflect this one graph to form this one? And the crux of that is, do you understand the difference between reflecting about the line y equals to x and the line x equals to 0 and the line y equals to 0, which are what? A y-axis and x-axis respectively. So yes, that is very cool and important. Right, good. So it has to be 2 over 3 and 8. I'm glad we are catching this. All right. Now, how would we calculate the value of b? Now, at this point, you have two options, and I've deliberately dragged this question to make it last. Sometimes they actually make it the first question to say calculate the value of b, but I want to make it last because now you have two options, right? You can either find the value of b using the original, which is the log function, or you can find the value of b now using the inverse, which is the exponential function. Now, if we use the original, which is the log function, I need to see what happens here. In that case, the following happens. I will have, where am I going to write now? Okay, let's just add a new page. I know that f of x is equal to log x and the base is b. And I know that here I've got the 0.8 and 2 over 3. So if I use the original, I can literally go in the place of y, I will substitute a 2 over 3. And then in the place of x, I will substitute an 8. And then I've got a b here. Then you use your definition. You use your definition to do the following, to say b to the 2 over 3 must be somehow equal to 8. Now, you did sets hectically so last year, but you can then use your theory or your knowledge of sets to actually sort this out. Did I say 2 over 3? Okay. Yes, that's that. So now, how one would solve this is someone would cube this, right? And if you're going to cube this side, then you're going to cube that side. And I'm just taking it step by step so that you see what cubing does. Cubing leaves you with an b squared here. And of course, on the right-hand side, it's an 8 cubed. And I don't know my cubes so well. It's after 4 after all. So you'll forgive me. But 8 cubed is 8 times 8 times 8. I don't know if that's going to be a 512. But then from here, you can find the square root of 512. That's one way to go about it. Another way to go about it will be, well, let me take the exponential. If I take the exponential, in other words, the inverse, we said the inverse will be b to the x. And I think this is one which most of you will relate to. Now, when you take this one, please take note, then your coordinates will be 2 over 3 and 8. So just watch out there. So it's very important that you note the switch here. So then you get to have 8 is equal to b to the 2 over 3, which is essentially the same thing that you had with the exponential, but obviously with the exponential, the catch is here. I know how students are not always confident with the switch from log to exponential, but I know if I ask you to substitute coordinates in exponential form, that you can do, and it will be pretty easy. So then from here, you're gonna pretty much do the exact same thing. All right, so this is the long and the short of it, of dealing with the exponential and the logarithm. What we're gonna do in our next session, we're actually gonna discuss the parabola in depth, and we're gonna check what about the inverse of a parabola. We're gonna investigate whether the inverse of a parabola is a function or not, and we will look possibly at the definition of a function and maybe go further there. So, but then for today, that will be about it. Let's not do information overload, but let me also give you a chance to go complete your homework and so forth. But yeah, thanks guys for coming through, and those questions that which you asked, that's really good. I'm glad, because then it does show that you are engaged and actually making sense of what we are doing here. Thank you. We meet again next Sunday then around 5 p.m. I think. Yeah. And yeah, we'll take it from there. Thank you. Cheers.